This is number 2 from the mock AP exam number 4. We have function f that is continuous on the closed interval from -4 all the way to 3. The graph of f consists of 3 line segments and a semicircle. We have h of x as defined as the definite integral from -1 to x of f of t dt. So this is showing us something here. This is telling us what the relationship is between f and h. So f is really sitting at a derivative level below h because the antiderivative of f will bring it up to the h level. And if we want to find h prime, we can push this through the derivative procedure, which is really second fundamental theorem of calculus. And we can see that these two operations undo each other. Plug the x in for the t, and we have f of x. So this is important, even if the problem doesn't explicitly tell you. We need to recognize that this notation indicates that f is really the h prime graph. Okay, so we're really staring at the derivative graph for h. Part A, find the x-coordinate of each point of inflection for the graph of h. Well, if this is the h prime graph, then the point of inflection are just going to be the peaks and valleys of the h prime graph, right? And since that's the case, then our points of inflections will be at -2, x equals -2. We're only asked to find the x-coordinate at 0, at x equals 0, and at x equals 1. Since h double prime changes signs from positive to negative. Part B, find the maximum value of h on the closed interval from -4 to 3. Justify your answer. Anytime these are kind of trigger words here for us to recognize, this is really telling students to try and recall extreme value theorem and to apply that extreme value theorem. Okay? That is how we justify our answer, to show the work that goes along with extreme value theorem. So extreme value theorem, or EVT, basically tells us that if we're trying to find an absolute max or absolute min, we're going to be considering the endpoints and the critical points, in this case relative max and relative min. Because we're only asked to find the absolute max, we only need to test endpoints and relative max. We don't have to test relative mins, or we don't test critical points that are neither relative max or relative mins. Okay, so if we're looking at the h prime graph, we need to understand that we can label our h prime graph accordingly, right? Anything above the x-axis will indicate where my h prime positive slope. Anything below is going to be where my slope is going to be negative. Anything on the x-axis is where my h prime is going to be 0. That's my critical point. And so we know the critical points is going to be at -1 and 1. Anything to the left of -1, we see h prime is positive. So we have positive slope. We reach the slope of 0. Negative slope from -1 to 1. Hit a slope of 0, and then negative slope again. So we have an idea how the graph is going to rise and fall. Okay. So now we're going to apply extreme value theorem. That means we're going to test the endpoints, and we're going to test the relative max. So all this is going to go into our h function here. This is how we're going to find those order pairs. So we have h of -4. We're going to find h of -1, find h of 3. So to find h of -4, we're going to enter in exactly as we see it. We're going to plug the x into the upper bound. So we go from -1 to -4, but I like to read the graph from left to right, so I'm going to flip the bounds and make sure I change the sign. So as I change the sign, I get -4 to -1. This will give me 2 plus 2 plus 3 halves, which is 5.5. There's a negative in front. I forgot to add that. So we have a negative 5.5. Okay, negative 5.5. If I plug -1 in, my bounds are the same, so that will give me 0. My bounds are the same. I haven't moved at all, so it's going to be 0. And in my other endpoint, h of 3, from -1 to 3, there's no need to convert the bounds. I'm just going to do negative pi over 2 minus 1, and that's going to give me negative 2.5. Okay. By the way we find these values is we have to look at the graph in relation to the x-axis. So that's something I skipped over. This is what I used to fill in. I'm looking at all the regions between the graph and the x-axis, and here I just split everything up into either rectangles or triangles, either 1/2 base times height or length times width. For the semicircle is pi over 2 r squared, since it's pi r squared divided by 2, and here also 1/2 base times height. All these are nicely above the x-axis, so these are all positive values. This region is below the x-axis, so I have to make sure I adjust that to be negative. And this is also below the x-axis, so that's also negative. Right. And as I total the values, these are what I'm going to be using to decide what is my absolute max and absolute min. Now, I made a mistake here, so negative 5.5 with 0 with negative 2.5, the absolute max is going to be 0. So I need to change this here. Absolute max of h of x on negative 4, 3 is 0 at x equals negative 1. Okay. Okay. All right, part C. Find h double prime of 2. Justify your answer. Well, we already used second theorem to show that f is really sitting at the h prime level. So if I take the derivative one more down, h double prime, this will turn itself into f prime. So if we know this is our relationship between h and f, then h double prime of 2 is just going to be f prime of 2. And f prime of 2, since this is the f graph, we just want to know what the slope, the rate of change of this line segment is. And if I just do rise over run, I can go down 1 over 2, or I can do change in y over change in x. Either way, we see the slope of that line is going to be negative 1/2. Okay. All right, let's look at part D. Part D says let p of x be defined as what's shown below. And we want to know, is our function p continuous at x equals 1? Show the work leading to your answers. So let's refresh our memory with continuity conditions. So continuity conditions, first off, does the point exist? Second, does the limit exist? And sometimes we may have to push down to looking at one-sided limits and see if they are in agreement. And thirdly, does the point exist where the limit exists? All right. So we know our point, our x value, our center of focus is going to be at 1. So we're going to start stepping through our conditions here. So p of 1. P of 1 is going to be defined with the first piecewise because we see the equal sign. So we'll plug 1 into the first piecewise function. F of 1 plus 1. F of 1, we look at our graph here. F of 1 is simply going to be 0. So 0 plus 1 is equal to 1. So move on to the second condition. Does the limit exist? We see that we have a graph that is split on either side of 1, so we're going to have to rely on one side limit. So we'll do limit as x approaches 1 from the left side of 1 for this piecewise, and we'll do limit as x approaches 1 from the right side of 1 for this piecewise. Okay. So now, all we do, the notations are showing one side limit, but as we plug in, we're not going to use decimals. Okay, we're just plugging in 1, we're just plugging in 1, and see where that takes us. So f of 1 again is 0, 0 plus 1 is 1. So from the left side, the graph is approaching a y value of 1. From the right side, if we plug 1 in for x, we get 1 plus 2, which is 3. F of 3, we look at our graph here. F of 3 is going to be a negative 1. So negative 1 minus 0, it's going to be negative 1. Now, we see there's an issue, right? The limit, the one-side limit, are not moving towards the same y value. So there is, these don't agree, so therefore we can say that the limit does not exist. And if the limit doesn't exist, then we know it can't, we don't have to look at the third condition. We already know where it's going to fail. It's going to fail in that second condition. So our function is not continuous at x equals 1, since there is a non-removable discontinuity at x equals 1. due to the fact that the limit does not exist. All right, part E. Between -4 and 3, a particle moves along the x-axis. The velocity of the particle is represented by the equation v of t equals f of t. So our f of t function, this is basically, we're going to treat this like our velocity function. Find the acceleration of the particle at t equals 5/2. Is the velocity of the particle increasing or decreasing or neither? Justify our answer. So we want to know, is the velocity of the particle changing? And is it increasing or decreasing? We have to recognize this this phrasing here. This is not the same thing as is the speed increasing or decreasing. So we see the word velocity, but really this phrasing is talking about acceleration. If the velocity is increasing or decreasing, it's purely talking about the rate of change of velocity, and that is just at the acceleration level. So the acceleration is just going to be the derivative, or in this case, the slope of the velocity function. So 5/2 is right around right at 2.5. So we see that the slope of this line segment is going to be down 1/2, slope of -1/2. So our acceleration at this point is -1/2. Now, since acceleration is negative, then we can make that conclusion that velocity must be decreasing since acceleration is negative. I do want to point us to something that looks very similar. And if the problem has said, is speed increasing or decreasing, then we have to look at information from the velocity and acceleration. Okay, so let's solve this problem just to see the distinction between these two types. We will have to compare the signs between velocity and acceleration, and we see that velocity at 5/2 is obviously below the x-axis, so that's going to be a negative velocity. But then the acceleration is also negative because we see a negative slope. So then we can conclude that because velocity is negative and acceleration is negative, our speed is therefore going to be increasing. But I want us to make sure we see that distinction between the phrasing of this problem. If it's just velocity increasing, decreasing, we don't look at velocity, we just look at acceleration to make our conclusion. And then if it's speed increasing, decreasing, then we look at velocity and acceleration.